All right, hello. Welcome to another snowy evening recording. This is lecture 8, where I'm going to talk about something called the query release problem and a particular instance of the problem called interval queries. And then we're going to see a really cool, clever algorithm for answering interval queries with differential privacy called the binary tree mechanism, which comes up in a lot of settings, not just interval queries. It's a very useful mechanism, and we're going to talk about this very useful problem and this very useful mechanism. So the query release problem is really just capturing the motivating problem we used when we talked about reconstruction, which was how can an organization like the Census Bureau release a big table of summary statistics about their data. So if you look at this table, remember the census collects lots of demographic information, and they want to release tables like this one with statistics like how many members of my data set identified as female, or how many members of the data set identified as a Black or African American female, or how many are 64 or over. Okay, so there's lots of individual statistics in this table, and we can capture releasing a table like this as a big collection of little simple statistics. So for today, I'm just going to focus on the counts. So I'm only going to be interested in count statistics, but the types of ideas that go into this apply to releasing, medians of little subpopulations and means, but we're just going to think about counts. So the types of queries in this column all have the following form. So my data set is x1 through xn, and every xi comes from some domain u. And each entry of this table is a query of the following form. So I'm going to call this a count query, or sometimes a statistical query, sometimes a linear query. It goes by lots of names. We also call it a count statistic or a linear statistic. But it asks for the sum of all the people in the data set of phi of xi, where phi is some function that takes an element of the universe and maps it to 0, 1. Okay, so all this is saying is we have some 0, 1 valued function phi. So it takes in a person's data and tells us if they're in the subset. You can think of phi as saying, is this person a Black or African American female? 1 if yes, 0 if no. And we're going to sum this function up over all of the records in the data set, and that's going to tell us how many people answered yes to the question. Okay, so this is the type of query we're interested in. And in the query release problem, what we're given is a bunch of queries f1 through fk, and we want a set of answers a1 through ak such that every answer is close to the corresponding query. So max over j equals 1 to k of fj of x minus aj should be smaller than alpha n, where I'm going to call this the error. And of course, we want a differentially private algorithm that takes the data set x and produces the answers a1 through ak. All right, if we didn't have differential privacy, of course, I could just evaluate the answers, but we want to do this with differential privacy. So epsilon differential privacy. Okay, so each of these queries is individually something very simple. It basically corresponds to like one number in this table. But if we can answer lots of these queries, then we're getting interesting tables, right? We're getting lots of information about the data set, and we're able to produce these summary tables like the one you see on the right. Okay, so depending on the specific queries, we can represent lots of interesting things this way. So we can represent lots of interesting summary tables or types of summary statistics as answering a big collection of these count or statistical or linear queries on the data set. Okay, so this problem is something that's gotten a lot of attention and has sort of driven a lot of the advances in the field. So a lot of the advances can be thought of as coming from studying this problem and trying to find algorithms that give us answers with less error. All right, so let's take our problem and let's think about like a baseline for a moment. So, well, this isn't going to work. Okay, so remember we're given F1 through Fk, want A1 through AK, such that max j of jx minus aj is small. So what's the baseline algorithm? Well, it's to use the Laplace mechanism, right? These are real valued statistics. I mean, they're integer valued, but so they're real valued. So we can try to use the Laplace mechanism. So the baseline mechanism is the Laplace. And let's think about how to use the Laplace mechanism for this problem. So I can write down one function that takes a data set and outputs a vector of all the answers. Okay, so that function is going to be, f of x outputs f1 of x, f2 of x, fk of x. And what the sensitivity of the function is, right, it's how much changing one data point can change this vector in the L1 norm. Okay, so if I change one point, I can change the answer to every query by plus or minus 1. So the most I can change the vector in L1 norm is by k times 1, so k. Okay, so f is a k-sensitive function. So if this went by a little fast, I would recommend taking a moment to pause and think about why the sensitivity of this function is at most k. Right? And one thing to point out, right, this is no matter what the queries are. For any queries. So for any count queries, for any queries of our form. So I haven't used anything about the set of queries in question yet, and this is a k-sensitive function. Okay, so if z1 through zk are drawn IID from Laplace with parameter k over epsilon, then the vector a1 equals f1 of x plus z1, ak equals fk of x plus zk is eps dp. Okay, so if I release like this whole list where I've taken the true answer and added Laplace noise, I have epsilon dp. Okay, that's our analysis of the Laplace mechanism. And now the max error in expectation is just the maximum of the Laplace variables, which is order 1 over epsilon times k log k. All right, so this is a baseline solution. It's differentially private, and we answer all queries with error about k over epsilon, just a little bit bigger, k log k over epsilon. All right, and there are ways to remove the log factor, so I'm not going to focus on it. But the problem, right, is that this solution, it's very simple, it's differentially private, but the amount of error is growing with the number of queries. It's in fact growing more than linearly in the number of queries. Okay, so if we want to release a big table, we're quickly going to have to add tons of error, right? K over epsilon is going to be too big if this table is quite big, is like an interesting set of queries. So we'd like to come up with ways to do better. And we're going to see lots of ways to do better a little later on in the course. But what we're going to focus on for now is just one special case of this problem where we can use more structure of the queries to try to do better. Okay, so we're going to come back to query release as kind of a general problem. But what I want to do is I want to show you one example of the query release problem where we can do a lot better than this baseline solution. And give some taste of like how we can do it by exploiting structure in the queries. And what we're going to see is one instance of the query release problem that's kind of interesting on its own right. So let's get to it. So the example are what I'm calling interval queries. So here, the domain of the data is just some set of integers, up to some number d. Okay, so like the universe is going to be the integers 1 through d, and I'm sometimes going to denote this as d in square brackets. It's just a little easier than writing 1 through d. And the data set is x, where everybody gets a number up through d, and there's n of them. And each of the queries specifies a range of numbers. So each query specifies a range of numbers, like s to t, and asks how many people's data lies in that interval. So for example, I can ask a query, fst of x, which is the number of people I, such that xi is between s and t. And here, what I've depicted is an instance of this problem where the domain is size 8. So the data points are numbers between 1 and 8. And the size of the data set is 15. So each of these purple points is one of the points in the data set, and there's 15 purple points. And maybe I want to ask the query, what is how many of these people have a number between 5 and 7? So this query here is like f5 through 7, and you can see that the answer to the query is 2, 3, 7. So there's 7 data points in here. Okay, so that's an interval query. And what we'd like to do is we'd like to answer the whole set of interval queries. Okay, so goal, compute answers to all interval queries. All right, so that's what we'd like to do. And first, let's see, why would we want to do this? Okay, so why are interval queries useful? So if I'm given some set of data that takes a real number, so let's say something like a set of ages. These are real numbers between about 0 and 125, give or take. Right? Maybe what I want to do with the data is I want to compute some summary of that distribution of the ages. So like I want to know for all people who are enrolled in my training program, what is the distribution of their ages? And one way of summarizing that distribution is through something called the cumulative distribution function. And this function takes in a number t, and it outputs the fraction of users in the data that have data below t. So for example, phi of 6 would be, how many people in this data set, or what fraction of people in this data set have data at most 6. And the answer to that query is 8/15, so a little bigger than a half. All right. So the cumulative distribution function is like this pink step function. It says, how many people, what fraction of the data lies below this point. So, at 1, the answer is 3, 3/15 of the data. At 2, the answer is also 3/15 of the data. At 3, it becomes 5/15 of the data. At 5, it becomes 7/15 of the data. And once we get up to 8, it's 1. Everybody is at most 8 by definition. And the cumulative distribution function is a really useful way of summarizing the data, and it's of course implied by having all the intervals. So every point on this cumulative distribution function is just asking how many people fall in the interval 1 to t. So in fact, it's a strict subset of all the information we get out of the intervals. And if I have the cumulative distribution function, I can compute things like quantiles. So like the Q quantile is something like, for what number t are Qn people below t. So for example, the median is like the 0.5 quantile of the data, and the, people talk about things like the 75th percentile, that's saying, what is the number t such that 75% of the people are younger than age t, if this represents ages. Okay, so the quantiles are essentially asking for the inverse of the cumulative distribution function, although we have to be a little careful because the way I've defined the data is discrete, so it's not clear how you invert something that's not continuous and not invertible. But we can make suitable definitions for how you would define the inverse of this step function. And the median is like phi inverse of a half. So for example, you can think of the median by saying, let me draw the horizontal line corresponding to 1/2, figure out where it hits the pink line, and then sort of drop that down. And in this case, I get 6. And 6 is a reasonable choice of the median in the sense that there are 8 points that are at most 6 and 7 points that are greater than 6. So again, because things are not continuous, how you break ties is important, but 6 is the median of this data set. Okay, so if I have the answers to interval queries, I can get nice summaries of the data, like the cumulative distribution function, the median, the 75th percentile, and so on and so forth. So it's a useful way of summarizing data that's where everyone's represented by a real number or an integer, so data on a line. Okay, so this is a useful thing to do. And it's, of course, an instance of the query release problem. So first of all, let me go back to defining the problem. Okay, so this is an instance of query release because every query f s comma t is just asking for the, takes your data and spits out a 1 if your data is between s and t, and a 0 otherwise, and we sum that up over all of the records. So this is an instance of query release. So what's our baseline? All right, well, our baseline is that this is a query release with d plus 1 choose 2 statistics. Okay, so there's d plus 1 choose 2 intervals to consider. And that's about d squared. So it's order d squared. So just using the Laplace mechanism, gives error order 1 over epsilon d squared log d. All right, so if we have a domain of size d, we can answer all of these queries with error about d squared log d. All right, so that seems maybe like, I don't know how to say whether that's good or bad, but if you think about something with a big domain, like maybe not age, which has a domain of 125, although 125 squared is still kind of a big number. But think of this as something like income, where if income is in dollars, incomes range from 0 up to millions, right? And so if the error is growing proportional to a million squared, that's not going to give us good accuracy. So we'd like a solution that has better scaling with d. And the first thing you might think is, maybe there's something special about this family of statistics that means that actually, if I look at the entire vector of interval queries, maybe the sensitivity is lower. Okay, so the first thing maybe to kind of convince yourself of is that this actually cannot be improved just by, cannot be improved because the sensitivity is omega d squared. So if we want to use Laplace noise, we have to add noise d squared. Now, when I say can't be improved, what I mean is can't be improved for the Laplace mechanism. Like we can't just argue that the sensitivity is lower and add Laplace noise with a lower magnitude. Okay, so as we'll see, you can actually get a better algorithm. I just mean that it's not like we can just add less noise. We have to actually change the algorithm in some more meaningful way. Okay, so let's see kind of our first interesting example of query release, where we can improve the error not by reducing the sensitivity, but by actually just using some more of the structure of the queries. So kind of the intuitive idea of how we're going to get a better algorithm is we're not going to try to answer all the interval queries directly. All right, so there's like d squared queries we want to answer. But the first thing you can probably notice, right, is that some of the queries are kind of related to one another, right? Like if I want to know the answer to the query, how many people have answers below 5, that's not entirely distinct from how many people have answers below 4. There's like some relationship between those queries. They're kind of asking about similar sets of individuals. So maybe we can start by answering a small number of queries, like an easier set of queries, and then trying to somehow like recover the answers to the remaining queries. All right, so in particular, what we're going to do is we're going to pick a subset of all of the interval queries. We're just going to answer the subset. All right, so we're going to start with like a simpler query release problem where we only answer a subset. We're going to answer that subset with less noise, and then we're going to try to combine the answers to get the other interval queries that we haven't answered. So what's the subset going to be? So step 1, answer all queries f1 through t for t between 1 and d. Okay, so these are like just the queries where the interval is from 1 to t. We're not going to allow you to specify s. We're just going to let you specify t, and you get everything below t. So this is like just the cumulative distribution function and nothing else. All right, and this is now just a set of d queries. So using Laplace, we've already won, right? Like just because we've reduced our set of queries down to d instead of d squared. So what we get is a bunch of answers such that the difference between our query and the answer is just order 1 over epsilon d log d. Not d squared, just d log d. Now, we don't have all the queries, so we're not done. What are we going to do? Well, look at this query that I actually want. I want to know how many people live between 5 and 7. All right, But I don't have the answer to 5 and 7. But what I can do is I can say, well, look, what if I start by getting all the people between 1 and 7? Okay, so this is like f1 through 7. And the answer to this query contains all the people I actually care about who live between who are 5, 6, and 7. So it's all those 7 people. Plus it's these other 4 people who have the values 1 or 3. So I want to kind of make those people go away. So what if I just figure out how many of those people there are and subtract them off? And that's just the query f1 through 4, which is a query I have. Okay, so the difference between the answers to these two queries is exactly the thing I care about. Okay, so what I have is exactly, what I have is exactly that the thing I care about, f5 through 7, is f1 through 7 minus f1 through 4. Okay, and more generally, fs comma t is 1 comma t minus 1 s minus 1. Okay, so I can get any interval query by taking the difference between 2 of the queries that I've already answered. And okay, so for every do not allow that. Right, so for every query that I don't have the answer to, let's let a of s comma t be a of 1 comma t minus a of 1 comma s minus 1. I guess I should be just a little more precise. So the ones I don't have the answers to are the ones where s is at least 2. Okay, so now I have an answer to every query. One thing to note that's very important is that this is just a post-processing step. I'm not actually touching the data anymore, so I'm allowed to post-process however I want. I've already got privacy in step 1. I'm never looking at the data again. I'm just using the answers that are already private, and I'm post-processing. So post-processing preserves epsilon dp. That's good. And now, what's the error? Well, for every query, I have that the difference is the Laplace noise I had on one query minus the Laplace noise I had on the other query. And by the triangle inequality, that's just less than the magnitude of the two noises. And all I'm doing is I'm summing up the magnitude of two noise variables. And we said that every one of these noise variables is going to be O of 1 over epsilon times d log d. So if I add up two of them, I still get order 1 over epsilon d log d. I just double the error at worst. All right, so this is still order 1 over epsilon d log d, and that's my final, error guarantee. Okay, so I've reduced the error for all of my d squared interval queries down from d squared to about d. Okay, so I basically got about a quadratic improvement. And remember, the key idea here is to find an easier set of queries to answer. In our case, that easier set of queries was a subset of all the queries, but in principle, I don't have to use interval queries. I could use some other set of queries. But I found an easier set of queries, a smaller set of queries, and took my queries and I combined them in some way to get all the remaining queries I care about. All right, so there was some trade-offs here. Basically, I found a small set of queries. That meant I could use less noise, but I had to then add up 2 of them to get the answers I want. But reducing the number of queries was such a dramatic improvement that I could afford to double the noise by summing up 2 queries. So it was okay. It was a win overall. So, the obvious question is maybe I can find like an even easier set of queries. So something that's even easier, maybe even smaller, maybe just easier, and do a more clever way of combining and get even better trade-offs. And that's what we'll see in the next video. We're going to get an algorithm for answering all the interval queries where we actually reduce the noise down not just quadratically, but exponentially. We're going to get something that's polynomial in the log of d. So that's going to be the next video, and I will be back in a minute.